The January 20th paper in the Astronomical Journal is fueling our interest in planetary exploration and stimulating a healthy debate that's part of the scientific process. I couldn't be more pleased about what's happening. You know, it's all about starting the process that could lead to an exciting result. It is not, however, the detection of a new planet. It's too early to say with certainty that there is a so-called Planet X out there beyond Neptune's orbit in the farthest reaches of our solar system. Something strange is unfolding. A mysterious force appears to be influencing icy objects, causing them to cluster in unusual orbits that can't be explained by the gravitational pull of the known planets. Scientists believe this phenomenon could be the result of a massive hidden planet, often referred to as Planet 9. First proposed in 2016, the idea of this elusive world has captivated astronomers. Interestingly, this wouldn't be the first time a planet was predicted through mathematics alone. Both Neptune and Pluto were discovered after their gravitational effects were calculated long before they were observed through a telescope. Astronomers first noticed irregularities in Uranus's orbit and later unusual patterns in the orbits of Kuiper belt objects, which led to the discovery of distant worlds. Now, a century later, we find ourselves in a similar situation with Planet 9, continuing the fascinating tradition of using mathematical predictions to uncover hidden celestial bodies. Some researchers speculate that Planet 9 might have been a rogue planet captured by the Sun's gravity, while others propose it formed from the same disk of gas and dust that created the rest of the solar system. If it exists, Planet 9 is estimated to be 10 times the mass of Earth and orbit the Sun at an astonishing distance of 400 to 800 astronomical units, AU. 400 to 800 times the distance between Earth and the Sun. Astronomers are eagerly searching for evidence of this elusive planet, employing powerful telescopes and advanced computer models to trace its gravitational influence and piece together its mystery. After years of observing the sky, solving intricate equations, and running sophisticated computer simulations, astronomers now have some of the strongest evidence yet for the existence of Planet 9. This discovery adds a thrilling new chapter to the mystery of our solar system's hidden planet. But what exactly have researchers uncovered in their search for Planet 9? And if we can detect exoplanets located hundreds of trillions of miles away, why has spotting this potential giant right in our cosmic neighborhood been so difficult, even with some of the world's most powerful telescopes? Most intriguing of all, if Planet 9 does exist, how did it end up so far from the rest of the solar system? Before we dive into the details, don't forget to subscribe for regular updates on the latest space discoveries. While the idea of Planet 9 was first proposed in 2016, its story actually began much earlier, shortly after the discovery of Uranus in 1781. Over the years, astronomers noticed something unusual. Uranus wasn't moving exactly as their calculations predicted. It seemed to speed up and slow down in its orbit, suggesting the presence of an unseen force influencing it. In the 1840s, two mathematicians, Urbain Le Verrier in France and John Couch-Adams in England, independently hypothesized that these irregularities could be caused by the gravitational pull of an unknown planet. Using complex mathematics, they predicted the location of this hidden world, a bold proposition based entirely on calculations rather than direct observation. Le Verrier sent his predictions to Johann Galle, an astronomer at the Berlin Observatory. On the night of September 23, 1846, Galle and his assistant pointed their telescope to the region of the sky Le Verrier had pinpointed. To their amazement, they discovered Neptune on their very first night of searching, remarkably close to where the calculations had predicted. This groundbreaking achievement marked the first time a planet was discovered through mathematical prediction rather than chance observation. After Neptune's discovery, astronomers believed they had completed the inventory of the solar system's major planets. But as they tracked Neptune's orbit, they noticed subtle, persistent deviations, similar to those observed with Uranus, hinting once again at the possible influence of another hidden object. Building on the success of using gravitational influences to predict Neptune's existence based on Uranus's orbit, astronomers wondered if the same method could uncover yet another distant planet. This search ultimately led to the discovery of Pluto on February 18, 1930. Clyde Tombaugh, a young astronomer at the Lowell Observatory, spotted a faint, distant object moving against the backdrop of stars, confirming the existence of a new celestial body. Initially celebrated as the long-sought Planet X, Pluto was later found to be far smaller than anticipated. Its mass was insufficient to explain the gravitational anomalies observed in the orbits of Uranus and Neptune, suggesting that something even larger and more distant remained undiscovered beyond Neptune's orbit. In 1951, Dutch-American astronomer Gerard Kuiper proposed a groundbreaking idea: Pluto wasn't alone. He theorized the existence of a vast population of icy objects beyond Neptune, forming what we now call the Kuiper Belt. Pluto, as it turned out, was just one of many such objects. Confirmation of Kuiper's hypothesis came decades later in 1992, when astronomers David Jewitt and Jane Liu discovered 1992 QB1, the first identified Kuiper Belt object, KBO. This groundbreaking observation provided direct evidence of a region populated by countless icy bodies, fulfilling Kuiper's prediction and reshaping our understanding of the outer solar system. The discovery of 1992 QB1 was quickly followed by the identification of hundreds more KBOs throughout the 1990s and 2000s, firmly establishing the Kuiper Belt as a major component of our solar system. As more objects were found beyond Neptune, the term trans-Neptunian objects, TNOs, was introduced to describe all celestial bodies orbiting the Sun at an average distance greater than Neptune's orbit, approximately 30 astronomical units AU. An AU is the average distance between Earth and the Sun, roughly 150 million kilometers, 93 million miles. With a growing catalog of known KBOs, the idea of a single massive planet X began to lose traction. Astronomers proposed that the combined gravitational influence of many smaller bodies in the Kuiper Belt could account for the observed irregularities in Neptune's orbit. However, a surprising discovery in 2003 reignited interest in the search for a hidden planet. Astronomers identified Sedna, a distant TNO with an unusually elongated orbit. Sedna's aphelion, the farthest point in its orbit from the Sun, is an astonishing 937 Australian dollars, making it one of the widest orbits known in the solar system. This unexpected finding shifted the focus back to the possibility of a massive, unseen Planet 9 influencing the orbits of distant objects like Sedna. That's 31 times the aphelion of Pluto and 19 times that of Neptune. Sedna's perihelion, or closest approach to the Sun, is just 76 Australian dollars. In contrast, Pluto's entire orbit averages only 248 years, while Sedna takes an incredible 11,400 years to complete one orbit around the Sun. This is not only unusual but also raises two major questions. First, if Sedna formed in its current location, it would suggest that the Sun's protoplanetary disk extended to at least 75 Australian dollars, an upper limit far beyond what is typically accepted. Second, for Sedna to have formed through the accretion of smaller bodies, its original orbit would have needed to be nearly circular. A highly elliptical orbit like Sedna's would have resulted in violent collisions, preventing the aggregation of material necessary to form a large body. This implies that Sedna's elongated orbit must have been shaped by a gravitational interaction with a massive object after it formed. The discovery of 2003 EL61 in 2005 further deepened this mystery. 2003 EL61, another large TNO, also has a highly elliptical orbit with a perihelion of about 38 Australian dollars and an aphelion of roughly 97 Australian dollars. In the following years, astronomers discovered even more extreme TNOs, ETNOs, which led to one of the most compelling pieces of evidence for Planet 9. The orbits of these ETNOs revealed something peculiar. To explain, imagine scattering dozens of marbles on a flat surface. Under normal circumstances, you'd expect the marbles to spread out randomly. However, in the case of ETNOs, their orbits seem to cluster in a way that defies randomness, pointing to the gravitational influence of a massive, unseen object. If any of the marbles are oddly clustered in a specific area, it suggests that some force or influence is pulling them together. This analogy mirrors what astronomers have observed with extreme trans-Neptunian objects, ETNOs. Instead of their orbits being randomly dispersed as one might expect, these distant objects exhibit a surprising clustering pattern. Normally, if TNOs were orbiting randomly, their perihelion points, their closest approaches to the Sun, would be scattered across the sky. However, these perihelion points are unusually bunched together in a single region. This clustering is highly unusual and strongly suggests that a common factor is influencing their orbits. Moreover, the long axis of their orbits, the lines connecting their perihelion and aphelion, farthest points from the Sun, are aligned in a way that is statistically improbable to occur by chance. This alignment provides additional evidence of an external force at play, possibly the gravitational pull of a massive, unseen planet. The consistent orientation of these orbits strongly supports the idea that Planet 9 is shaping the paths of these distant objects. The discoveries of Sedna, 2003 EL61, 2012 EP113, and other TNOs added momentum to the Planet 9 hypothesis. In January 2016, astronomers Konstantin Batygin and Mike Brown published a groundbreaking study analyzing the orbits of 6 distant TNOs. Their work concluded that the unusual orbital patterns could best be explained by the gravitational influence of an undiscovered planet. According to their calculations, this hypothetical planet 9 would be about 10 times the mass of Earth and orbit the Sun in a highly elliptical path, with a distance ranging from 400 to 800 astronomical units. Unlike Neptune, which was discovered quickly based on precise mathematical predictions, the search for Planet 9 has proven far more challenging due to several key factors. First, it is an immense distance. Planet 9 is thought to be 102 times farther from Earth than Pluto, residing in a region where sunlight is extremely faint. At such a distance, the planet would reflect very little light, making it almost invisible to even the most advanced telescopes. Second, it's likely an elliptical orbit. If Planet 9 spends the majority of its time in the farthest, darkest parts of its orbit, it would be even dimmer and more challenging to detect. This combination of extreme distance and an elongated orbit significantly hampers efforts to locate it. The third challenge is the vast area of the sky where Planet 9 might be hiding. Its potential location spans a wide region, requiring astronomers to painstakingly scan enormous sections of the sky, often repeating and verifying observations to ensure nothing is overlooked. Finally, the planet's slow movement across the sky adds to the difficulty. At such a great distance, Planet 9 would appear to move very gradually against the background of stars, making it harder to distinguish from other celestial objects. Because of its immense distance from the Sun, Planet 9 moves very slowly against the background stars. This slow movement makes it difficult to distinguish from stationary stars, requiring astronomers to conduct prolonged and repeated observations. Potential candidates must be carefully tracked over time to confirm they are moving objects rather than fixed stars. Given these challenges, simulations have become an indispensable tool in the search for Planet 9. Simulations allow researchers to model complex systems and predict behaviors that are difficult or impossible to observe directly. These models have provided some of the strongest statistical evidence supporting the existence of Planet 9. The orbits of TNOs are not stable over millions of years. Neptune's strong gravitational influence can gradually alter their paths, scattering them into different regions or ejecting them entirely from the solar system. This dynamic process frequently pushes TNOs into orbits that intersect with Neptune. To study this further, a research team designed simulations based on the presumed conditions for the formation of the Oort cloud, a distant spherical shell of icy bodies surrounding the solar system. The Oort cloud is thought to extend from roughly 2,000 to 100,000 astronomical units, AU, from the Sun. The researchers selected TNOs with perihelia greater than 38 Australian dollars and semi-major axes ranging from 100 to 5,000 Australian dollars. Simulating the behavior of 2,000 particles, they ran 2 sets of simulations, one that included the hypothesized Planet 9 and its predicted location and another without it. The results revealed that Planet 9 could significantly influence the orbits of certain TNOs through the direct coupling of the Runge lens vector, which describes the shape and orientation of an orbit under gravitational forces. The direction of this vector determines the orientation of the orbit's ellipse, while its magnitude is directly related to the orbital eccentricity. A zero Runge lens vector corresponds to a circular orbit, while non-zero values indicate elliptical orbits. Planet 9's presence was shown to stretch these orbits further and alter their inclination angles. The simulations demonstrated key differences between the scenarios. Without Planet 9, TNOs were less likely to come close to Neptune. The number of TNOs approaching Neptune sharply declined with increasing distance, peaking around 30 Australian dollars. However, when Planet 9 was included, close approaches to Neptune occurred more consistently across a wider range of distances, starting from about 16 Australian dollars. To validate these findings, the team conducted a statistical analysis comparing the simulation results to real-world data. They accounted for observational biases and matched the simulations with 17 known TNOs that have perihelia less than 30 Australian dollars and semi-major axes greater than 100 Australian dollars. The comparison strongly supported the model that included Planet 9, yielding a much higher likelihood of 0.41 compared to just 0.0034 for the model without Planet 9. These findings provide compelling evidence for the existence of this distant, elusive planet. The significant difference in probabilities suggests that the model including Planet 9 aligns more closely with the observed behaviors of TNOs, implying that Planet 9 plays a key role in shaping their orbits. Later this decade, the Vera Ceed-Rubin Observatory in Chile will begin operations with its advanced 8.4-meter telescope, designed for nightly all-sky surveys. This observatory will build on recent findings, including those supporting the existence of Planet 9, by closely monitoring the movements of distant TNOs. If these objects consistently show patterns of being further from the Sun beyond about 16 Australian dollars, as predicted by the Planet 9 model, it could provide a vital clue to the planet's presence. With cutting-edge technology and groundbreaking research, this effort could significantly enhance our understanding of the solar system's outer regions and perhaps lead to the long-awaited confirmation of Planet 9. Recently, the James Webb Space Telescope also measured the rate of the universe's expansion, revealing a major crisis in cosmology and indicating a fundamental flaw in our current model of the universe. If you missed this exciting discovery, be sure to catch up on the details and don't forget to like and subscribe for more updates. See you in the next video.